And we are going to conclude today's set of sessions with the talk by Jacob and Kevin, who's going to talk about the software delivery building blocks at Datadog.
Hi, and welcome to Software Delivery Building Blocks at Datadog. My name is Jacob LeGrone, and I work as a team lead on the software delivery platform at Datadog. I'm joined today by Kevin.
Hi, I'm Kevin. I'm part of the data reliability engineering team. We are responsible for the reliability and safety of most of the data stores at Datadog.
Today we'll be talking about why we built an internal software delivery platform. We'll go over some of the design considerations we had in mind during this process. We'll talk about the building blocks that we came up with and some of the trade-offs that we balanced along the way. And finally, we'll explore a case study of how we extended the platform to manage a complex stateful application on Kubernetes. Before we go further, it's helpful to have some context about Datadog. Datadog is an observability platform that provides full visibility across your organization. We span end-to-end from your infrastructure and network to your applications and services, all the way to your end users. This enables folks across ops, development, and security in the business to have a shared understanding of your systems and the ability to immediately resolve problems when they arise. As Datadog has grown as a company, it became more apparent that we needed to create a software delivery platform to match our scale. We operate many stateful systems that process trillions of events per day. We run across cloud providers and regions, and much of our infrastructure is on Kubernetes, where we handle thousands of deployments per day. On top of that, we maintain over 400 integrations with third-party systems. So our main objective in building a software delivery platform was to help Datadog engineers stay product-focused and continuously deliver features while still keeping up with the pace of growth and complexity of our environments. One of the first factors we decided to optimize for was safety. We know that there will always be unforeseen incidents, but as much as possible, we'd like to help our users avoid easy mistakes and catch issues early on by standardizing around practices like progressive rollouts, testing at scale, and having automated quality gates in place. Another priority was extensibility. Because we have over 400 plus integrations and target multiple cloud providers, we need to be able to support a large variety of deployment tooling and target runtime platforms. We want to allow developers to be able to extend our platform while still encouraging reuse and minimizing boilerplate. Of course, our platform itself must be reliable, and perhaps most importantly, we knew that we needed to optimize for user experience. Ideally, we'd like software delivery at Datadog to resemble what Rico Mariani called the pit of success. To paraphrase, rather than making our users go through an arduous journey to solve their problems, they should simply fall into winning practices by using our platform and frameworks. Over time, we arrived at a design that looks like this. The base building block that all Datadog engineers interact with is application bundles. These make up our basic application definition, including all of the configuration files, container images, and deployment tools necessary to manage the lifecycle of an application. At the next level up, Synap workflows execute application bundles and progressively roll out changes across environments and failure domains. As the third building block, deploy lifecycle hooks are not always necessary, but can be very useful for coordinating simple application-specific logic at deploy time. And finally, we have temporal workflows, which can be used to orchestrate lower-level building blocks and interact with external systems when necessary. These building blocks are ordered from least to most commonly used by engineers, which is also correlated with their relative complexity and flexibility. Now we'll take a closer look at each of these. A CNAB, or Cloud Native Application Bundle, includes the configuration and deployment tooling needed to manage the lifecycle of an application. These are the most basic building blocks of the platform. Every engineer at Datadog that deploys a service to Kubernetes packages their manifests or Helm chart into a bundle and interacts with the platform to create instances of their application in any of our Kubernetes clusters. Application bundles are key to the extensibility of the platform because they can package other software too, like Terraform modules. Because every bundle exposes a standard interface for managing the lifecycle of its application, we can build unified user experiences around these objects for operations like diffing a deployment or performing a rollback when something goes wrong. CNAB workflows are the second building block, and these are how engineers roll out their changes in production. These provide a declarative interface for specifying the deployment topology for an application and for orchestrating the rollout of changes across environments and failure domains, including what can be regions, clusters, availability zones, or application shards. The declarative API and composability of workflows is designed to be high scale and light on complexity. This contributes to the safety of the platform by helping keep cognitive overhead low while we wrangle more smaller deployment units, and allows teams to fine-tune the balance between rollout speed and risk. The third building block is the concept of deployment lifecycle hooks. These are another way for engineers to extend the platform by specifying application logic to be executed before, during, or after an application instance is updated, and helps them avoid the need for complex consensus algorithms during these phases. In Kubernetes, we define these as job resources with a special annotation that's picked up on by our deployment tooling, and engineers only need to provide a container image to execute. Some example use cases for lifecycle hooks include triggering a database backup, applying migrations, running end-to-end test suites, or monitoring traffic and failing if anomalous errors are detected. Finally, the last and most powerful building block is temporal workflows. Temporal is an open source project that allows engineers to write fault-oblivious control flow and business logic in the programming language of their choice. We rely on Temporal as the backbone of the rest of our software delivery platform, and also expose it for engineering teams when the other building blocks don't fully meet their use cases. Compared to Synap workflows, Temporal does have some trade-offs, in that the imperative programming model makes it hard to build tooling around things like dry runs describing what a workflow will do. And there is some additional operational complexity associated with managing the deployment and registration of temporal workers that teams maintain. However, we have found that Temporal can be a great complement to Synap workflows, especially when managing complex stateful applications or long-running operational tasks, like migrating data across nodes or interacting with asynchronous real-world processes, like opening and merging a pull request or notifying a human and waiting for manual judgment. To walk us through an example of how all these pieces fit together for a real use case, I'll turn it over to Kevin now, and he can talk about how we leverage some of these building blocks to manage Kafka on Kubernetes.
So at Datadog, we're using Kafka a lot, and we have many clusters. If you don't know what Kafka is, it's an event logging system. Without going into details, you can imagine it as a publish-subscribe service or a sort of message queue service that stores the message on the local disk. Our Kafka clusters run on Kubernetes and on different cloud providers. We have different characteristics such as the instance type, the cluster size, the version being used. All of these clusters are managed by the data reliability team, which I'm part of. We are taking care of the lifecycle of the clusters, provisioning them, doing version upgrade, day-to-day operational tasks, capacity planning, decommissioning, and so on. And we are making sure that the number of clusters and their size can grow without having to grow our team size linearly. As mentioned, all of these clusters are running in Kubernetes. We use Helm charts to define our clusters and their characteristics. In order to deploy them, we started with Spinnaker pipelines. One of the major issues that we had was that we had to specify a lot of parameters when running our pipelines, which cluster, version, image, namespace, and so on, which was quite error-prone. I ended up deploying a cluster in the wrong Kubernetes namespace a couple of times, and then you have to do cleanups and such. Managing the pipeline was also a high maintenance job. It ended up not being the right tool for the job, but it served us well for the time we used it. We eventually migrated to the deployment of our Kafka clusters to the Synap installation that Jacob just presented. We benefited from the declarative approach and the resource management done by Synap. Creating and deleting cluster is now way simpler since we just give to Synap the state of the Kubernetes resources and it figures out how to deploy them. We also build automation on top of Synap. We now have tools that automatically generate the definition of our Kafka clusters and trigger a Synap workflow that will deploy full Kafka clusters. So Kafka itself, its dependencies, and the set of tools that we use to manage Kafka. While we use Synap to deploy our clusters, and have their resource reach a given state, Kafka itself needs a bit more when doing operations on it. For instance, if we want to migrate a cluster to a new type of machines, we have to do more than just adding n pods to the stateful set. We'll need to tell Kafka to rebalance the data across its pod. And for that, we'll use both Temporal and Synap. So to illustrate that, I'll show you how we perform this instance type of upgrade, where we move from type A to type B, which has more disk space, for instance. We'll do that by creating a new pool with different instance type, move the topic data to it, and then tear down the old pool of machines. We need to be correct when doing that, as we don't want to accidentally remove the old pool before all of the data is gone from it. So this is an example of cluster definition that we actually use. You can see that we define a pool of 3 brokers using the default instance type. Let's say that this cluster is getting full and we want to move to a different type of instance that has like more disk space. From our toolbox, which is a pod that runs alongside our Kafka cluster, we can run this exact command, which will trigger a temporal workflow to move the map, so the topic and all of its data running on pool 3 to a new pool 4 that has 3 hosts with high3en large instance type. Here, moving a map means moving all the topics associated with it and their data to this new set of hosts that will be in pool 4. The workflow starts by creating a pull request that edits the YAML configuration file that I showed you. The member of the team has to review it, approve it, and merge a pull request. The automation then resumes and will kick off a Synap deployment with this new version of the YAML file. Synap will take care of the deployment, and this will create 3 additional pods running on i3en large machines. Once the pods are up and ready, we'll use the Kafka tools to tell it to move the data from pool 3 that we are now draining onto pool 4. So you can see the result here with disk utilization. In that case, we can first notice the diurnal pattern with the disk utilization going up around like 21 o'clock. And we decided to replace the instance with a type that fit our needs. So you can see the new brokers that join the cluster and start getting new data. So that's the first line going straight up. And you can see the previous lines that have their disk utilization going down because the data is moved onto this new set of hosts. Eventually, we had to add new machines, so you can see a second set of lines a bit later that is also going up and also join the cluster. It is when we scale up a pool, so it's a different workflow that is quite similar to the one that I'm presenting. It's just extending the current set of machine and rebalancing the data on top of it. Finally, when the data has been moved, it's empty and create a new pull request that removes the old pool. Once this is approved and merged, we eventually create a new Synap deployment to clean up the Kubernetes resources and remove the associated machines. And that's it. So besides starting the command and reviewing and approving pull requests, which still on purpose require a human interaction, we've been able to automate that process end to end. And this is what the actual process looks like with all the details. So it can be quite long and complicated. And we were able to extend Synap to fully integrate with it in our day-to-day operational workflows. And it saves us a lot of time, as you can see. Not requiring a human to perform this action while still benefiting from all the safety mechanism that we have from our tools is a big win for us.
All right, thanks, Kevin. So to wrap up, we ended up building a software delivery platform at Datadog in order to meet our own requirements around the safety, extensibility, reliability, user experience, and scale that we have around software delivery. We found that there is a place for both declarative deployment workflows in the form of Synap and also imperative operational workflows with Temporal when we need to manage more complex operations. If you'd like to learn more about Synap or Temporal, please visit their respective websites. And of course, we're also hiring, so please come check us out if any of this sounds interesting to you. Thank you.
Thank you so much, Kevin and Jacob, for sharing the way you scale continuous delivery at Datadog. It's definitely a very interesting approach, especially the combination of declarative and imperative nature